I'm the founder and CEO of Conway Innovations. Been researching on generative AI for past couple of years, and our company Conway Innovations is building foundation models and also fine-tuning models that are actually kind of used in medical sector. So my specialization is more on the computer vision, particularly on the vision language model side, vision transformer side, and also on large language models. Our main focus is on what the on the edge AI systems. That's the AI that can actually run on devices like on PCs, on your smartphones, on embedding systems. So this class is much more on the first of all on the theoretical part, along with an active inference part on the coding side also. So we'll be discussing about it will be like more on an engaging level of conversation that I would like to propose more. You have to be more active in this class. So I'll be discussing the whole architecture of one of the latest vision language model called Gemma 4. Gemma is it's a foundation model from Google. You know, Gemini. They open sourced. Google has been open sourcing a lot of sub-variant models like Gemma in Hugging Face. So we'll be discussing the Gemma 4 architecture, how it actually works, how these vision encoders works, how it actually combined with vision language, I mean the transformers architecture, and at the end how it actually generating the output. And to be frank, I need to get an understanding how good you are at the transformer side. I think you guys are actually been into language models for like the past couple of days, and you guys have some foundation on top of it. So to get an understanding, I need to get some of you guys can explain how a large language model works. Particularly, we are more focusing on the vision language side. So we have the vision encoder there, we have a language model there. You're combining together to get a final output. But the thing is that you should have an understanding of how transformers, I mean the large language models works, how the how the just to be a understanding how the text is actually kind of processed in the transformers architecture. That's what I want to know. If anyone wants to just speak, just unmute yourself or raise your hand. I will.
Like understanding the context of the text.
Perfect. What are the layers? What's the first layer of a transformer? Can anyone can say about that part? This is just to get an understanding how much you're. I mean, you can also write it on the chat box if you are so much worried about speaking. Yeah, there's an encoder is there. Then the next layer, decoder. Yeah, but there's some additional layers are there. Obviously, we call it an encoder decoder, but it's purely encoder architecture. Sorry, decoder only architecture. So for that, transformers are we call as a decoder only. Yeah, feedback layer is there. Because a vision language model is a combination of vision encoder and the transformers. So transformers should be very clear when you're dealing with vision language models. Should I have to brief about a language model from my side, or should I have to just go for LLM side? Yeah, input layer processing is there. I mean, you guys are went to the transformers architecture side, right? So you can just explain what are the layers. So we have the encoder is there, there's a feedback layer is there, there's input layer processing is there. This output layer is there. Cool. I think, should I have to just rough out what the transformers or the model large language model architecture is? Not the vanilla one, but more on the on modern one. Is it needed? If you have some confusion about the whole pipeline of how text is actually generated, if it's needed, just type yes. Otherwise, we can just type no. Then we can go for the full. I have a couple of slides and I have a whiteboard with me, so I can explain it if you want, or else we can just go for the full machine language model architecture. Okay. Can I just anyone just mention about that part? If it's needed, just type yes, or else we can just go for. Okay. Let me brief about what language model is. I think we have time, so we have 2 hours, right? So just to get an understanding, I'm going to share the screen. Let it take that aside. Okay. Works on the one, pardon me on that. Yeah, text generation models. Yes. Let me just skin around how this model works. Then we'll get an understanding how VLM works in this particular situation. So the first, obviously, if you're giving high, the first part is obviously go for a tokenization, and you have a sentence like hi there. Each of these will be assigned with a token ID. We call it a token ID, and it's just a random numbers like say 18, 19. Okay. So the first part is obviously we call this as a tokenization. That is, the high there will be split into high and there. and each of them will be assigned with a number called 18 or 90, say 26. Okay, so 18 represent high and 26 represent there. Machine doesn't understand, words. So let me just take high. This will be 18 will be converted to, this is we call tokenization, this part. That is splitting the words, the sentences into characters, into words. We call this as word level tokenization. There's a different level of tokenization. There is word level tokenization, character level tokenization, sub-tokenization, which we call as a byte pair encodings. That is, it's an iterative process. We don't have that much time to explain how PP works. It's an iterative training process. You can use sentence keys to make it. So it will actually split that sentence into subwords. This is one of the simplest example we call word level tokenization. That is splitting word level tokenization. That is splitting the sentences into individual words. So high there. High is converted to high is assigned with a number called tokenization ID or tokenization word level ID or tokenization ID in symbol or TID. And this will converted to, we call it as an embedding or the vectors. This 18 will be converted to say 0 0.1, 0 0.2, 0 0.3. Okay. This is we called as an embedding layer. Then the next part, for the most modern large language model, we use this rotary positional encoding. How many guys heard of ROP? Because ROP is one of the most important part in our example. So the next part is we have vanilla transformer where it converted to position vector value. That is, position vectors will be added. Okay, for vanilla, I think we can look into vanilla part. So vanilla transformers, that is a 2017 paper called Attention is All You Need. In that paper, there's introduced a positional encoding vector called PE or PE positional encoding, which signifies two equations, sine POS divided by 10,000. I think you guys have familiarized with. I'm just skimming this part really fast. POS by 10,000 raised to 2i by d. Similarly, cos POS divided by 10,000 raised to 2i by d. What is d? D is the dimensionality of the model, which is 1, 2, 3. And I represents the vector's position in here in the embedding. So here I equal to 0, then 1, then 2. Okay. POS means the position of the original sentence, original word. Here it's 0. We are representing high. So just the idea is to add a positional vector value. See, the machine doesn't understand where the high is actually located. So the whole idea is to add a vector value such that the model understands that high is at the 0th position. Got the idea? So you are converting, you're getting the, you're splitting the sentences into words. You're converting that to token ID. These token IDs are converted to embedding vectors, and the dimension is 3. Then you're adding positional vector values. Okay, that's the equation is signed for even position, and this is for the odd position, which means we can calculate this part. So here POS is obviously 0. Okay. So the POS is 0, which means this equation become sine whatever this sine 0. What is sine 0? 0. So similarly, this will become cos 0, which is 1. Got it? Which means it doesn't matter any value that's you're giving. So here, the 2i by d, the I is a location that we are looking into. So the I is 0 means it's the even position case. This is for this. Say same repeated for this. Which means this is for the even position vector that we'll be adding. See, 0 means an even number. and this is for the odd number, that is I equal to 1. So you're just getting after, so high converted to 18, then you have embedding layer 0.1, 0.2, 0.3. Then you are added a positional vector value, which will become, we add 0 with 0.1, that is 0.1. We add 1 with 0.2, that 1.2. Then again 0.3. That's it. That's how the positional encoding for the vanilla transformers works. Is this part clear? Just have any kind of doubt, just tell me. Because this is very important as we are moving towards vision language model, we combine this with a vision encoder. So you will need to understand how an LLM works. Do you guys actually know this part? And anyone raise your hand? That's you already know this part. Or you can type on the comment section that you have any kind of doubts or something like that. New to this topic. Okay. Just type new if you don't know this topic, new in the comment section. Okay. Everyone type new if you don't know this topic. Type new if you don't know this topic really well. We have a couple of new here. Other people already know this topic? Okay, so we have a couple of people who doesn't know this. Let me brief it out. Okay, so yeah, we'll discuss. Don't know exactly. Cool. Don't worry, we will say it. So you guys understand the concept, right? So a transformers is basically a text generation. We can use it a lot of purpose, text generation, classification, and all purposes. So particularly for text generation use case, the whole idea is to understand the word's meanings, right? How an AI, how mathematically a word is actually understood by an AI, by a computer. Have you ever actually think about that? How it actually know, like, hello there, how can I assist you today? Or difference between this and say, I actually hate mathematics. How it actually understand these sentences, how it actually understand the difference between the sentences. So the logic is about, the main part is actually about extracting features. Every AI is actually extracting features. So the first part is obviously converting the word. Say hi, you have hi. You just hi there, say example for our case, hi there. You split that sentence to each individual words. Then you assign a token ID. Say hi assigned with 18. Then it's very important to assign token ID. I will be explaining later why we need a token ID. So hi is assigned 18. Then it will be converted to vectors like 0.1, 0.2, 0.3, which represents hi. Okay, which represents 18. Then the next question comes. Where is hi is actually located? Is it located at the third position? No, it's actually located at the 0th position, right? Then you add another set of vectors that we call a positional vectors. Say 0.1, 0.2, 0.3. 0.1 you add with 0. Then 0.2 you add with 1. 0.3 add with 0. That is 0, 1, 0, 1, 0, 1. That's for the 0th positional vector values. 0, 1, 0, 1, 0, 1. That equation is signed POS by 10,000 raised to 2i by d. I means that embedding vectors locations. If it's even position, it's sign. If it's odd, this is cos. That's it. Got the understanding? Just be with this part. This is for the vanilla transformers. There's a difference between this and modern language models. Is this part clear? If it's clear, just type yes. Cool. So you have the word, you convert it to embedding vectors, you add positional vectors. Now you have the position, that is the high. Now the next question comes into the equation, what the high actually represents. Okay. So the next part is obviously what? Self-attention. Obviously, it's self-attention, right? So it's in self-attention, uh, you have positional vectors like here like 1.2, 1.3, and we can represent like x, right? This x, that is 0.1, 1.2, 0.3 is going to self-attention. Okay. There comes the interesting part, query key value. Can anyone say, unmute yourself and say what is actually this query key and value means? Anyone raise your hand just, or type it if you are like, don't want to talk about stuff like that. Just type what Q, K, and V means. Just unmute yourself and just say it. If it's for, yeah, it's fine. If it's error, it's completely fine. Whatever you're understanding, just unmute yourself and just talk, or maybe just type in the comment section. Okay, I think yeah, actually, yeah, query search, correct. And what does key means? There's some difference. It's not actually search. I will explain it. So imagine like let me give you an example. I think that will give you an overall idea for this concept. So imagine you are going for a party. Say you are going for a party. Yeah, you're going to a party. The party is happening. You are in Bangalore, so you have like a lot of partying happening right in weekends, right? And you're going there. You know dancing, so you know dancing. So you're going there. Yeah. So this is you, and this is all people here in the party club. And you're asking this guy A, and you have asking this guy B a question. So do you know dancing? That's your query. Do you know dancing? Guy A says, yeah, I know dancing. So you got this guy A. So he said, I know dancing. I know it. And you just go to guy B and he said, say, I don't know dancing. Now you know the guy A know dancing and B doesn't know dancing. Now you need to focus on this guy. And you ask question about like what kind of dance you know. Is it like contemporary, or maybe in Western, or maybe in classical? And he's saying that I know Western dancing. And you're asking about different variations, different styles. And he say all the details about what he know. That's the V. So query means the one thing that actually you're mainly focusing on. That's your query. That's do you know dancing. That's you're mainly focusing on, right? To get the answer. Key is the identifier. You know what we say, that you got this guy based on, we call it we simply say it's a brief description. So you know that this guy is actually know it. So you lock on this guy. Okay. Then comes the value, that is detailed description. You know, like all the Western style, or maybe if you know classical, what kind of classical dance, Bharatanatyam, Mohiniyattam, all these variations are there, right? And you get more about the information. Okay. So let me give it this with an example sentence. Let's say cat sat on mat. Okay, which is the most important word in the sentence is obviously cat, right? This is more important. You need to give bigger value to this cat, say 100. Sat on mat. Stat is a second word. Say simply, for example, 50, you're giving mat with 40, and this is 10. So you're giving max value to the most important word in the sentence. So how will you actually do it? Okay, so the query you're focusing on is cat. So that's the first query. That's query cat. You go to sat, you go to on, you go to mat, and then you again comes to cat. So this is sat, and see how much actually it relates. You don't to get every meaning of sat. Sat means there may be other meanings. For this context, how it actually related. That is key. And getting more details out of it, that is V. So for example, like a guy, this guy, for this example, let me take this guy, singing, this guy, like drawing, this guy, like he's a mathematical professor, he know maths. But in this context, you don't need to know all this stuff. You only need to know whether he know dancing, right? Similarly, for this context only, you need to get more information. That's where the value coming into the question. You don't need to get every information out of it, but based on the query and key, how much actually it's related to query, this that, and get most information out of it. How much it's actually related to query and get maximum information out of it, not all the information, but specific to this context. Got it? Just got the idea about query key value, right? Should be a very detailed session. I cannot take every bit of it, but let's skim it through the idea about query key value. This is the most foundational principle of modern large language model, including transformers like Gemini, Cloud, ChatGPT, visual language models, the standard diffusion models, even the video generation model like the VO3 or the latest Chinese variations. Everything is actually used as a foundational query key value principle. To understand query key values, to understand the modern large language model. So the thing that we are focusing on is we call query. The generic description that we are actually going for each individual is called key, and we get the idea like, yeah, we need to connect this guy. Then we get the value, that's the detailed description. So like the Dr. Gevorgis title said, it's key is like a label. So you connected this label, you get the information out of it that we call value. Then how will you calculate the output? You need to get the output, right? You need to get some kind of information. So the equation comes. So we have here. This is after positional encoding a value that is added with 1, 0, 1, 0. We added that like before. Then goes to the self-attention equation. First we will do is to multiply query and key. Sometimes the query key values, every time, I mean, literally these are we called as the tensors or matrices. Sometimes its values can be, a matrix A and B can only be multiplied only if and only if like A 3 by 2 and we have B should be 2 by 3, right? This should be, this column of the first matrix should be match the row of the second matrix, right? This is row by column and row by column, right? So sometimes the problem is query has like matrix like A3 by 2 and K may have 2 by 3. And you need to transpose the matrix, right? Transpose is simply speaking, you have a matrix like 1, 2, 3, 4, and when you transpose the matrix, it's become 1, 2, 3, 4, right? Sometimes it's needed, sometimes when we don't need it. So just row by column transformation is only needed if and only if the matrix multiplication is not possible. So what the first part in calculation of the attention matrices, I mean the final output matrix, is query key transpose. Then what you do is to divide this with the dimension through dk. Okay. Then you wrap it with softmax function. Then you make a dot product with v. So the equation comes with softmax qk transpose divided by root dk dot v. This is standard self-attention output equation. This is we called attention score. This gives how much important should be given to each individual vectors or the each individual words in the sentences. Higher the QK transpose value, more the attention. So this is very important QK transpose. So do you know how softmax works? You guys know that, right? The standard activation function. So softmax is just, if you have a vector, say 1, 2, simple, like you have 2 rows and single column, 2 by 1 matrix. What softmax will do is to, so softmax of A is, so softmax of A is same level, like e raised to 1 divided by e raised to 1 plus, sorry, e raised to 1 plus e raised to 2. Similarly, e raised to 2 divided by e raised to 1 plus e raised to 2. So the idea is to convert this to between 0 and 1, 0 not included and 1 included. So in between zeros and 1 values. Why we need to convert zeros and 1? Because just to make it more interesting. That's an open question for you guys. Just check it out. Why we need to convert this value to zeros and 1. Softmax QK. Why we need to apply softmax in the first place? It's a simple idea. Just an open question for you guys. Just to convert this value to. Why we can get it to like 1. It's very easy if it's a single like 1 only. E raised to 1 divided by e raised to 1 plus e raised to 2, or of the vector value 0. I mean here just 0 means e raised to 0 divided by e raised to 0 plus, that's e raised to 0. That means it's 1. So in that case, it becomes 1. But it may never become 0. It will become very close to 0, never become 0. So that's how softmax works. You have a matrix A, and when you apply the softmax, you just dividing each of the values. Like if it's 1, 2, you apply softmax, which will become e raised to 1 plus e raised to 1 divided by e raised to 1 plus e raised to 2. Similarly, e raised to 2 divided by this value, e raised to 1 plus e raised to 2. This is for any kind of matrix, right? Okay. So that's how the softmax function works. Cool. This is the main part. Then the vision language model part is much more simpler to understand if you know all this concept. Because that part we have a lot of slides are there and a lot of interesting things are there. We can take it like 3 to 4 p.m. We can actually discuss that part. Within this hour, we can much more discuss about the transformers architecture. So this part is actually cleared, right? Yeah, type. If you don't understand, just be my guest and raise your hand if you don't understand this concept. Or just type your like queries or questions in the message section. Because as we move forward, it's all based on this idea. Yeah, clear. We will wrap it up. Okay, don't worry about that part. But if you have any doubts right now, just type it on the comment section. Okay, so let me go for the next part. I know it's a bit boring, right? So we have a softmax here. You have this self-attention output here. Then high converter to 18. Then they are 0.1, 0.2. That's embedding layer 0.2, 0.3 with dimension 3. That is embedding layer. Then you apply positional encoding vectors 0.1, 1.2, and 0.3. Then this is positional encoding. Then you have a softmax application, that's softmax QK transpose divided by root dk dot phi. See, this Q of high is calculated based on this. This is X, right? The equation is like X multiplied by WQ. WQ means the trainable matrix. For most of the cases, it's a random matrix for before training. After training, it's obviously a constant matrix, right? We call this as a trainable matrix when we train the model. Otherwise, it's a fixed matrix, say like 1, 2, 3, 4. Similarly, KH means another X multiplied by WK, and VH means X multiplied by WV. That's it. And D means, 3. Then comes with the next equation that's called as a feed forward network, or the FFN layer. FFN is basically a simple idea, a very simple idea of acting, like giving non-linearity in the model. So it's basically a simple equation. We got ReLU, rectifier linear unit, multiplied by X. There is an interesting idea should be discussing here. I think we cannot discuss that much that part. But anyway, we call this at the W up plus beta multiplied by W down plus alpha. What is W up, W down? X, this is from here. But there's a interesting X coming into the equation. So if it's, we don't call it X, we call it H. H is actually a multiplication of X, that is this coming in here, plus the softmax output. I mean, the self-attention output, say X plus O is called as H. This is we called as a residual connection. Why we need to add a residual connection? That's positional encoding output plus the positional encoding output plus the softmax output. Sorry, the self-attention output. We are adding that to get more context to the ReLU, to the FFN layer. So this is the feed-forward network path. So the ReLU is just an activation function. You have this ReLU, we call this as ReLU, that's max 0x. Means if there's a matrix like 1 minus 1, when you apply ReLU, then the matrix become 1, 0. That's it. Anything that's negative becomes 0, right? We only need positive values. Then up projection is basically a matrix that kind of put that matrix into higher dimensional space to get more features. Then you again multiply with the down projection value. This will become like, it can be a 10 by 10 matrix. Maybe you again down with 4 by 4 matrix. So you push that value to a higher dimensional space, vector space. Then you again push down back to the common embedding space. The higher dimensional space, you can get more information. So you just expanding that, vector space to get more features. After extracting features, you again push back to this value. And beta and alpha are actually like smaller values, like 0.01. This is called as biases, smaller values. That's it. You got the idea, right? So let me, this is the idea. This is what your transformers means. Then there is layer normalization. We don't need to look into that part. So you have transformers, the modern language model, not modern, but more on the vanilla transformers. You have high, then there is you convert it to token ID, then you convert it to embedding vectors, then self-attention. After that, you get the vectors, right? You just place it on a bigger projection space. We call it projection matrices, and you get more features out of it. Then you again like down projected to the common embedding space. That's it. That's it. All you need. Then the next final part is obviously you only get you apply layer normalization. That's just normalizing the vectors. The next layer is obviously layer normalization. I'm not going to discuss about that part. This we call root mean square normalization, RMS norm. A lot of stuff is there. You don't need to discuss. Just to normalize it with a constant vector value. Say you divide everything with 18. That's it. You divide every vectors from the FFN layers to divided by a common number to get normalized the vectors. Just think about that kind of idea. What RMS norm doing? Just dividing everything with a common constant number. Then finally you will get what you get. A bunch of vectors, right? 0.8, 0.9, 0.3, say blah 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 blah. Then you again get to a final layer with some programming and programming logic. It will eject a number. It will eject say 24. So let's head back to the primary part, right? $26, right? So it will eject say 1826, say for example. So what is that? So you apply after layer normalization. There's a final layer. Layer normalization has to divide with a common number, and you get finally you get 26. So 26 means this is we called the final tokenized ID. We decode it, then we get there, right? So first part is tokenizing encoding. That is you converting high to 2018. And each of the words represents have a token ID. So transformers, what it actually does in general, or the chat GPT that you're speaking is actually, so when you type hi there, and hi represents 18 and there represents 24, 26. And when chat GPT is replying, this is called encoding. That is converting to a token ID. It will reply with say 24, 26, 27, 86, blah, blah, blah. 24 represents, say, how high. Sorry, high is 18, right? So 18, 26 means there, 27 means how, 86 means can. Hi there, how can I assist you today? So it's actually at the end, it actually, from the final layer, it ejects these numbers. And when you decode it, you get the answer. So the whole idea is encoding, decoding. But the main part is decoding. So that we call as a decoder only architecture, and the whole thing happens on that part. There's a lot of debates when we say like it has an encoding decoder, but the core idea is always about decoding. So this is how a large language model actually works. You got the idea, right? Is it clear?
Yes,
If
sir.
it's clear, we need to move on to the next phase about the visual language model. So the VLM is actually a combination of LLM and a vision encoder. So you need to get a greater understanding of large language model in order to understand vision language model. So what you understand is just an overall architecture of vanilla transformers. It's in 2017 paper called Attention is All You Need by Ashish Vaswani and his team from Google Brain. That has been changed a lot. A lot of stuff has been introduced. A lot of things has been introduced. Okay. So does everyone understand the concept? So yeah, like if you have like more than 100 people are here, I think it should be very clear. Let me just get an idea, like overview of what transformers of the modern language, vanilla language model means. You have how it actually trained is very interesting, right? You have we have to discuss a lot about how we train the model. We don't have that much time. I actually built a foundational model. Like you need to get a lot of data, then you need to define the optimizers, the what kind of optimizer do you have to use, and you have to set up the GPU, like data parallel processing, and a lot of stuff has to be done. So we don't go for that part. We are only looking to the forward pass. Forward pass is much means the inference part. You're going for like text generation. You have hi and you say hi, how can you assist you today? That's a forward pass. Then there is backward pass. That's how you train the model, like reducing the loss, using backpropagation, and using modern optimizers like AdamW, that is adaptive movement weight TK optimizers, much better than the stochastic gradient descent methods. And you guide the gradients to such that the loss will be minimum. So yeah, we are not going for that part. So just to get an understanding, what we discussed is the forward pass, where the transformers is actually generating an output. You have encoder, you have coastal encoding, the embedding layer, then the encoding layer, then the self attention feed forward and layer normalization, and you're getting the final output. So I think I cleared what the vanilla transformers means. Okay, cool. Then we need to go for one of the important part, the standard vision language model. It will be more on I think presentation, blah 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 stuff. So vision language models are pretty much a lot of complex stuff is there. This idea about creating grids and stuff like that, and all this blah 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 blah. So the modern variations of vision language models, particularly I think Gemma 3, uses much more simpler approaches. So you have an image, you split it into like we call as grids, then you flatten it, then you fed it to the transformers model. So this part I will explain with an example, and we will discuss the modern the Gemma 4 E2B variation and how it actually works from here onwards. I think from here onwards, we will discuss about the idea about combining vision with the transformers, the model language models. Okay, so you have a couple of ideas here. That's I think we can discuss from here the vision encoder for the highs of the model, which will be much more easier for you to understand. So the idea is actually, the first part is obviously the standard Gemma 3 architecture, and we will discuss what this actually means. These are all, like, if you want to know more about this part, I can share this like PDF and all this part, like this. But I think we can start from here. These are all the language model side. We don't need to discuss all this stuff. I think we can start from this layer, the vision encoder eyes of the model. So we have the code here also, right? We'll discuss it later, okay? With the Google Colab code. That's in here. Let me. Okay, so you know convolution, right? You guys know convolutional neural networks. I think all you guys are professors. I never. I mean, it's a very simple concept. The standard convolution. It's based on the convolution logic. Okay, so you have an image. Say you have an image. This image. Let me just erase it. All this stuff. This is the architecture of Gemma 3, the predecessor model of Gemma 4. Okay, I mean, it's kind of latest model, but now it's actually obsolete, kind of, but it works. So you have an image. How a transformers understand image? You have text, obviously. I've said text. You convert it to token, text tokenization. Give it to Gemma. And you obviously get the idea of the talk, like the what we call the question. This we call query. Then how will you actually understand an image? How the transformers understand image in the first place? So the idea is to kind of combine convolutional neural network CNN, get the numbers out of an image. Anything can be converted to numbers. A text can be converted to numbers. An audio can be converted to numbers using Mel spectrum. Anything actually converted to numbers. Only the only thing that machine understands is obviously numbers, right? So the logic is to convert this image to numbers, right? So how will actually do it? Okay, so you have image here. You make it like patches. Okay, then what you can do is to define a kernel of 14. Just try it, same 14. Kernel means, convolution. You have, if you take a grid, say 8 grid, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7, and 8. And 1, 2, 1, 2, 3, 4, 5, 6, 7, okay, 8. So it's an 8 by 8 grid, and you think of it like an image of a dog. Then 1, 1, 2, 3, 4, 1, 1, 2, 3, 4, right? 1, 2, 3, 4. So this part we called as a kernel of 4. Yeah, then you slide the kernel by, say, stride of 1. You just push that kernel to 1 pixel, and it will push to another like this left, then like that. Just imagine that way. So kernel means that grid that you will move through the image to get what we call as reduce the dimensionality of the model of the image. That we called as the kernel, and stride means how much you need to push, right? So here the kernel is 14, the stride is 14. That's a like defined value, right? For this model, Gemma 3 model, and a padding of 0. Padding means if it's like 9, you cannot get the ninth value. You just need to push it again. Like I think you're applying 8, right? Say for like you have grid of 13. You need to push like uh 13. I think 15 is fine. Yeah, 15. Then you need to push one more stride, one more like column, say something like a column, like we call this an additional side to get it all the grid, cover the all the grid. So you need to get padding of 1, maybe padding of 2, 3, 4, 5, in any kind of, you can add a number on it. So just to get all the information. So you have convolution is an interesting concept, and it's very basic concepts when it comes to like, deep learning. So you have kernel of 4, you have 14, stride of 14, and padding of 0. So the convolution output become, so the equation is this is h, and this is height and width of the model. So it's both height and width are equal. So he and w is equal to h. Both are same, right? 896, 896. So the equation like h minus k plus 2p divided by s plus 1. Here, the k and s are equal, right? So you can say h minus s plus t equal to 0. 2p means t equal to 0. And s plus 1, s, you can say like s plus 1 here. So the equation become h minus s by s, right? Here, k and s are equal. See, h minus k plus 2p divided by s plus 1. So h by s minus 1. So usually, we actually don't consider this plus 1 terms. If you don't need to consider, you can consider, but usually we can call this like h by s. So, so the equation is, since k and s are equal, we can either put it like k plus 1 to k, or this become k, this become k though. So the equation become h by k minus 1, right? Sorry, there's a different error. Okay, so the equation is not denominator side, there's an error. Okay, so the h minus plus 1 is not there. Sorry. Convolution output equation is the denominator side is not correct. Okay, so the output equation is h minus k plus 2p divided by s plus 1. So the equation is h minus k plus 2p divided by s plus 1. So this is this. I think it's not here. So this equation become h minus k plus 2p divided by k plus 1, which means h minus k plus 0 divided by k plus 1 is equal to h minus k divided by k plus 1, which is h by k minus 1 plus 1 h by k. That's it. That's how it actually works. Not this part. That's my part of my from my side. So the equation is here, both of them equal. Then that means h by k, that is 896 by 14, which is equal to 64. So you get what we get, convolution output as 64. Then that sent to this sigmoid loss for language image pre-training, which is an encoder. What it will do is to convert this to 1496 tokens. So the model is actually trained. This is vision encoder part. This we call the vision encoder part. What it will do is this will convert the 64, that we call convolution outputs, to 1496 tokens. So an encoder, obviously what we do is to convert into tokens and assign a number, right? then it will again, pool. I mean, average pooling is obviously you getting the average value out of it. So average pooling is again reduce the dimensionality and send into the Gemma 3 layers. So in here is actually more focused on the main layers of the transformers. I mean, kind of combining in the think of it like combining with all the uh, say, all the transformers ideology, right? Like you have like self attention layer is there, there's an FFN layer is there. You just fed the text and image into the language model. So the meaning of the image is here, the meaning of text is here. So the text plus image tokens are get fed to the language model. Got it. So instead of tokens only, you have the text, and that's it. So kind of combining the common embedding space, but moreover, the dimension will be equal and it can be easily added together. And that's it. Your text token added with the image token. So text token added with the image token. Fed it to the large language model and get the output. So image text token means the query. What is this? Tokenizer. That's it. Similarly, this is image tokenizer. So what it will do is, in general, a visual language model, you have an image. You need to tokenize it, right? Everything need to tokenize. So image tokenizer. This is done by an encoder. See, encoder, you can use a standard tokenizer encoders like byte pair encoding or image like text generation token. So in this case, we are using SIGLIP, sigmoid laws for language image pre-training. And the query is, what is it? This is similarly tokenized with like standard tokenizer like byte pair encoding. Then both of them are fed into, combined together and fed into LLM. That LLM is Gemma. Standard Gemma 3 LLM. So if you link into Gemma 3, you can see the tokenizer model here. Gemma 3 1B is actually a text generation model only. You need to get Gemma 3 4B, or I think Gemma 3 and 4B. No. Gemma 3 12B, let's say. Yeah, this is a vision model. You have a tokenizer model here. If you look into this part, this is we called as the layers. You can see MLP down projection layer, up projection, gate projection. This we called as MLPs of FFN layers. Down I said before. Have you remember that part? Down projection is actually projecting to down. That is the common embedding space. Up projection means you are pushing into high dimensional space. Gate is actually basically a gating mechanism, whether to go for up or maybe go for down. I mean, kind of, it's used in most of the time, it's used into training purposes. Usually not much used in the inference part, but nevertheless, it's here. Then there is, attention, query key values, projections here. Then again, this vision embeddings part. This is what I've said. This vision embedding is what vision encoding is what the image tokenization coming into the equation, right? So this is where the image get tokenized. This is where the text get tokenized. That is tokenizer.model. So this is a practical way of understanding. See, image tokenization happens within the model itself. It's not outside the model. But the text generation in the Gemma 3 basically uses a different tokenizer model as a separate from the original foundational model. So image generation happens in combination with the image tokenization happens in combination with the original foundation model. But the text tokenization is obviously go for separate model. So I will give the link to here, Gemma 3 12B model. Okay, so that's how it actually works. Let me brief it out one more time. So a vision language model like Gemma 3 works based on an image. You tokenize it with SIGLIP kind of Sigmod language, Sigmod loss functional language image pre-training, which is an encoder. And that you can see this, this is we called as the weight files. Okay, this we called as a weight file of safety tensor files. You can see all the layers, vision tower layers. You have that language model layer, multi-model projector is here, vision tower model is here. So multi-model protection is where the what we call the you can say it's a kind of common embedding space. You combine this image like tokens and text token in this multi-model projection space to get the final result. And vision tower vision and is basically what we call the SIGLIP here, Sigma logs for language image pre-training. I think doesn't mention about SIGLIP here. If you go to technical report, you may find it. Let's say, sorry, SIGLIP vision encoder, The language model treats image as a sequence of soft tokens encoded by sigmoid laws for language image pre-training at that SIGLIP. We reduce the inference cost of image processing, condensing the vision embedding into a fixed 256 vectors. The encoder works at a fixed resolution. So that means the whole idea about SIGLIP is about encoding the image part with using this vision encoder. Then you just combine in a common projection space to get the doesn't mention about projections. So this is the technical paper. You can actually reference the Gemma 3 report paper. You can just go on and read it. It's on the Hugging Face report, Gemma 3 report. Just a link to the paper. The technical report is there. You can go for it and read about how it actually works. So you can look into it. So yeah. So the Gemma 3 model architecture is like that. So the vision modality, you have the vision encoder model, a 400 million of the SIGLIP model. The Gemma 3 vision encoder, the pre-training, quantization of pre-training, computer core infrastructure, filtering, instruction fine-tuning. Then there is local and global attention. We will discuss it. Okay. Okay. Then we can go with our original part. See, this is what I'm saying. The decoder reads both text and image as one, which means you just fed into the large language model combining both the text and image tokens as one and just stream it to the model. I think most of these models, like previous models, combined in the common projection space. The Gemma 3 variant doesn't combine with, doesn't have that. You just stream it. Okay. So this is the idea about the vision and the vision encoder part. The idea about patches, vision tokens, then the soft tokens and ideas like that. I think we need to discuss. Per layer, no. Okay. We need to discuss some of the interesting ideas about, the ideas about, particularly in modern language models. The one thing is that we use this called as a hybrid attention mechanism. And the other thing is shared KV cache method. Then there is dual rope and group query attention. Okay, we need to discuss these ideas, which is very important when it comes to modern language models. Okay. So GQA is one of the most important aspects when it comes to language model, and similarly, rotary positional encoding, which kind of replaces the standard positional encoding that I've explained earlier. So we need to discuss first of all the ROP, then we need to discuss the query attention mechanism, then you have the shared KV cache mechanism. Okay. So I think first we need to discuss about, we need to discuss about the rotary positional encoding. Okay. So I think let's head back to our whiteboard. Cool. How many of you know it? Rotary positional encoding, RAW. Have you guys learned it in the previous section? I think if you learn it, it's much more easier for me to give the idea. Has anyone actually heard of it? If it is, just type yes. No, type no. If yes, if you heard it, just type yes. Rotary positional encoding. Otherwise, just type no. Others also just involved in the meeting. Yeah. Just type yes if you know rotary positional encoding. If you don't know, type no. Okay. Then we need to discuss what is ROP. ROP is one of the most important part in language models. I think we need to look into that very, very clearly. So if you look into, I think ROP is mentioned in probably in the configuration .json maybe. Yeah, here. Like, like ROP scaling, ROP type. There is like this part, right? We need to understand what is ROP. So ROP or rotary positional encoding. See, you have query and key, right? See, this is one of the most important part in a transformers as you're getting query key transpose to get the attention score, right? higher the attention score, more important to that word, right? So this is what makes the modern LLM to understand the word meanings, context, semantics, etc. So this thing has a problem. So when it comes to query, query is like x multiplied by wq, and k is x multiplied by wk, right? And you get a vector values, say 0 0.1, 0 0.2, 0 0.3, 0 0.4. And similarly, you get 0 0.8, 0 0.9, 0 0.4, 0 0.8. This is just for example, right? So this has a problem. So it's not like this one. It can be like x0, x1, x2, etc., 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 xn, up to xn. So when it comes to this, how will you actually get an understanding about the relationship between these two, and maybe like xn minus 1 and xn? To understand this, like this is in the 0th position, this may be in the 10,000 position, right? So it will be very difficult to get an understanding what this actually represents. So there introduce the idea about the we called it as a relative positional encoding. So absolute is basically have a limit, and we are introduced relative so that the long relationship between the vectors can actually be understood. So that's where this idea of ROP has been introduced. You actually rotate the query and key vectors. So rotation gives an understanding, more understanding on the semantics, on the or the meaning of the actual word. See, query may represents like cat. We need to get more meaning of cat. So sometimes it will be very difficult to get a lot of meaning out of it. So what we'll do is we rotate. So Q will be converted to Q rotated. K will be converted to K rotated. Then, I know you guys are actually very familiar with the idea about the Euler's equation and stuff like that. So for particularly for the imaginary coordinate system, you have the real x-axis and the imaginary y part, right? So you have a vector, like for example, you have a vector 1, 2 can be represented as 1 plus 2i or 2j if you want. So similarly for q, you have vectors like x0, x1, x2, etc. You make it as a pair, x0, x1, x2, x3, and x3, x4. Sorry, x4, x5. You make it as a pair. Now we just need to consider this pair, right? Let's take it here, x0, x1. So z equal to x0 plus I x1. Then when we rotate an imaginary vector, we get z e raised to I theta. If this query represents this one, represents high for the sentence hi there, this position is obviously 0, which means p equal to 0. So this equation becomes z e raised to I p theta, which is equal to z multiplied by e raised to I p theta means cos p theta plus I sine p theta. Okay. Z means, Z is zx0 plus ix1. Then you multiply it with cos p theta plus I sine p theta. When you multiply this together, you can actually get x0 cos p theta plus ix0 sine p theta, right? Then ix1 cos p theta plus I multiplied by I x1 sine p theta, right? Then you can you have x0 cos p theta, then x0 ix sine p theta, then ix1 cos p theta, then I multiplied by I sine p theta. So we need to take real and imaginary part, right? And two part, right? So that means you can take x0 cos p theta minus I multiplied by I is actually root minus 1, right? I square means -1. So I x1 sine theta plus I x0 sine p theta plus x1 cos p theta, which can be represented as cos p theta. If you remove the I part, cos p theta minus sine p theta, then sine p theta cos p theta multiplied by x1 x2, which is x1 rotated, x1 dash, x2 dash. Again, the final equation is something like this. x1 rotated, x1 dash, x2 rotated, x2 dash, which is equal to cos theta minus sine theta, sine theta, and cos theta. Here his p theta is there, p is there, p is there, p is there. x1, x2. Here if you miss p, you need to add p. Yeah, that's it. Theta means 1 by 10,000 raised to 2i by d. And p theta means p by 10,000 raised to 2i by d. And if you give that value, you will get the new rotated values. So the softmax equation become, so you have high, you convert into 18 like before, 0 0.1, 0 0.2, 0 0.3. Instead of the positional encoding, you directly go for self-attention with Q rotated, K rotated, transpose divided by root dk dot V. The standard positional encoding has been removed. Instead, we use Q rotated, similarly K rotated. Got it. So Q rotated means the same thing I have explained earlier, 0 0.1, 0 0.2, 0 0.3, blah, 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 blah. And it's very important, it should be even. And K rotated, K means this, 0 0.8, 0 0.8, similarly. And it should be rotated. The pairs are rotated. And the I means here 2i by d, this I is the rotated pair I, right? So if it is like K is like 0 0.1, 0 0.2, and 0 0.3, 0 0.4, these are pairs. So I is the pair location value, 0, this is 1, like that, not the individual x1, x2 values, right? So you rotate z to an angle theta, z dash, and we get more in-depth relative understanding when you apply softmax. These are actually proven, right? So this is what we call rotary, positional, encoding probe. Got it, right? I think that part has been cleared. So I think we can move on to our final part. That is this part, like group query attention or the GQA. See, we need to understand, I think, global and local attention. So you need to understand that part. So this is hybrid attention and local attention mechanism. And the idea is, I've said attention earlier, right? You have local attention, which only look into the local tokens, right? It will only take into like nearby tokens. Like if you take a 512 token window, it only took into 512 vectors. So it will only look into 512 token, and sliding window means it only like take 512 tokens at once, then go on to next tokens and next token and so on. And global means a full token will be taken at one time, but will be much more costlier. Taking it all at once will become query key transfers, which become much more larger number. Multiplying to larger matrices will cost a lot of computation. So it will be much more expensive. So what it will do is, for every seventh layer, you apply global attention for a total of 28 layers. So you have here 1, 2, 3, 4, 1, 2, 3, 4. Sorry, fifth position, you have like 7 layers, total in 7 layers, sorry. So in the fifth position, you give a global attention layer. Then again, 1, 2, 3, 4 local attention. Fifth, a global attention. 1, 2, 3, 4 local attention. Fifth, a global attention. So on, so on. Total of 28 plus 7, 35 layers in a 4:1 pattern. Like 4:1. 1, 2, 3, 4, 1. 1, 2, 3, 4, 1. 4:1. 4:1. 4:1. 4:1. Totaling 4, 8, 12, 16, 20, 24, 28 local layers, and 1, 2, 3, 4, 5, 6, 7 global layers. So why actually we need to mix? Local layers do most of the work cheaply, but for long range dependencies, we need global layers. But we cannot use full layers because that much more like computationally expensive. Now let's again go back to group query attention. So you have local layers, 2 query, and you have 1 KV. That is key value. And then we have 2 query, 1 KV, 2 query, 1 KV. For a particular like global layers, for local layers, it's like this. And for the global layers, you have 8 query, all taken into 2-dimensional KV. So you're taking everything together, that 8 query, and you double the dimension of the key value. So that's where the global layers come into the equation. So what the group query attention will do is actually kind of combine this together. Particularly in most of the cases, we actually, for this case, I think in the Gemma 4 case, for the local, we take every 2 query heads share 1 KV head, and globally, we take 8 query heads share 1 wider KV head. So this is the whole architecture of the group query attention mechanism. For local query part, local layers part, we take this logic. For global layers, we take this logic. So this is for the calculation part. Uh, See, query key value is one of the most important part, and KV is the one thing that you are getting the final result. See, query is the one thing that we are focusing on. Like I said, key is the generic description. That is like if someone not answering, that's the key part. The value is the one of the most deepest, predominant, I mean the most descriptive part. So the KV give the logic, I mean the full overview of whatever sentence actually means. So KV calculation is done using this logic, that is you're taking two queries, then you take one KV each of out of it. And global layers you take this way. So this is the grouped query attention or GQA mechanism that's used in that. I think this part, I think we covered standard drop only each layers. Rotates each query key vectors by an angle proportional to its position. Creates inside a 512 token window, relative position stays clean. That is that I have explained earlier. Proportional ROP or the PROP on global layers. Only the first 25 features pairs get position rotation. Let the model scale to 128K context without special drift. Why two ROPs? Position needs a different scale for nearby as far away as token. One encoding can be both fine grained and long range. So this part, we only take 25% of the features pairs get position rotation. So that means for the larger scale part, we don't need much of these like angles. I think this like like 0.25 can actually stretch it to that much position. Like I said, P is the position location value. For this particular case, I think you don't need to drift it a lot. For the local position, you can actually use the same method, but for the larger scale purposes, only the first 25% of the feature pairs get position rotation. Lets the model scale to 128K context without spatial drift. So that means only the 25 features are get rotated, and the rest of them are kind of scaled or don't get the rotation at all. Okay, cool. Then the final, I think let's move on to the final, more interesting, important part, that is shared KV cache method, in which the KV cache that we are actually calculating get kind of cached. I mean, you don't need to reuse every computational results in each of the layers. So first we compute the KV for the 15 layers. Then rest of the layers reuse the KV from earlier layer. So you don't need to compute every like values out of it. You only need to calculate what we called the couple of layers, like 15 layers or 16 layers, and then reuse it from there. If you have 35 layers, you can just use the 15 layers and then just use that previous layers values for the rest of the layers. So that's how you can actually reduce the memory outline. So this way, the LLMs can actually doesn't have that much of computation in the first place. It's not going to take a lot of time to generate the text when you have like adding more context, adding more follow-up questions. You don't need to compute every time. Then the final Google Colab, that is the practical stuff. I'm going to share the Colab link with you guys. You can try it on yourself. And, I'm gonna just post Colab link here. So we are using Google Gemma for E2B model. Like I said here, Gemma for E2B uses a kind of different, just a different vision language model. That is a vision transformer plus a 2D rotary positional encoding. The idea is to add a rotary positional encoding is to get the relative position values such that the accuracy will be much more increased by reducing the number of parameters of the model. But this is actually need to 150 parameters. I think the original Gemma 3 is 200 to 300 million parameter ones, something like that. But it's much higher than this one. So using this, actually, they reduce the model dimension, model's parameters by adding a 2D rotational, 2D ROP method here, a rotary positional method here. So 2D position encoding aware of row column works at any aspect ratio. So the idea is that, and I think let me give here. So the pooling I've said earlier, you just average the vector values using average, or adaptive pooling is there. There's an average pooling is there. That's it. Then you combine with text token with image token combined together and fed it to the language model to get the final answer. So brief it out. That's the purpose. And let's head back to our code, right? So the first part is obviously installing an upgraded version of transformers to get the Gemma 4. See, Gemma 3 and Gemma 4 doesn't have that much of a difference. Only the difference is you are using a vision encoder difference is there, that's using a vision transformers plus a 2D ROP architecture. Notice like a unified vision encoder like Sigma allows for language train. But it doesn't make much of a difference. But the difference makes when it comes to deploying it as a smaller models on your phone. It can be kind of quantized and deployed it on your PCs or on your phone, etc. So we are looking into this image and a vintage car. That's this image, right? And we are asking it to get the answers. So the first part is obviously you have the model ID. You are add a request to download the image. Pill means the pillow package. Okay, we need to upgrade the transformers. So processor is for the vision and vision part. I think sorry, text and the image part. So this is for the combining. Here the text is here. Here the image is here. You get the text. Process dot apply chat template means it's actually applying the template. Then you combine the inputs. Again, just print inputs to get the understanding. Yeah, print the input length. We need to restart the section. Since we already imported the transformers, it was gonna go through that. Model ID device map auto means it's using the CUDA if it's available. We have a runtime set it as the T4 GPU with 50 GB VRAM GPU user and torch data type auto. So we have image. Then this is the standard prompt, standard system prompt here. Then the user prompt. What is the image? Explain it briefly. You have the text. You have the applying the text. You can just print the text also, right? It's downloading the model. So you have the text and you have the input that is combining the text and images together, return it as a tensor file, return tensor as a Python file, then to model to device. That means it's actually giving to that the CUDA layers or the GPU layers to process it. Then the input lines, together just get the input lines. Then the model generate maximum token that is going to generate to 1024 for an hour. So from here. Then there is obviously then there is process dot decode means the decoding part in which it will decode the outputs. So you can print the outputs to get understanding if you want more debug statements. You can run it one more time. Interestingly, you can actually convert this to a GGO file, which we call this a LAM like quantized file that we actually run it on our own device. And there are like, and also the Google Light After conversion, you can actually use it for your mobile purposes. Probably there's an app, right? Google in Play Store, there's an app. Think, yeah, it's called Google AI Edge Gallery. You can search it on Play Store. Google AI Edge Gallery. Then use the model to inference on I think it text is only support. I don't know if it's support image, but you can run it offline. Like powerful models runs on your own device without ever need for internet connection. So just to go to Play Store and or maybe I don't know App Store. Just search for Google AI Edge Gallery. It has like a symbol of it, like 4 dots or something like that. It's for early access for running LLMs only on edge devices. Let me restart the section. You can always look into the GPU VRAM utilizations to see whether it's actually using GPU. You can see the GPU VRAM went up to 9.6. See, the model is actually, we call this as the mixture of expert models. And I think it doesn't use this denser or something. Yeah, it's an MOU. It's an MOU. I think it's an MOU. Let me verify it. Yeah, it's an MOE. That means mixture of expert model. We call this as an MOE models rather than a dense model. An MOE model means if it's have a 5G, it's actually 5 billion parameter model. Only around 2.3 billion is actually used for inference. And that saves a lot of computation. So you can see 5B model, but it's only saying like E2B model, like 2.3 billion. It's only used for inference. That's where the interesting part of MOE coming into the equations. It's think of like multiple FFN layers. So you have routing happens between like in the feed forward network. So kind of an agentic approach inside an FFN. Let's summarize that way. Yeah. So you can again print response here. So let's see some of the concepts. Let's see. So the text is what is the image? Explain briefly. So the input is the combination of image and it's in a tensor format and the text combined together. Input length is 298. The output tensor is this. Then you convert, decode it. This is output 0. We can print it. So you can see a lot of numbers here. Which means when you decode it, what this numbers actually means 2094 can actually decode it. You can independently decode each of this part if you want. So I have this, then you can just either you need to convert it to vectors, probably. Let's say it may throw an error. Let's say it's a string. Yeah, that's an ID. So it should be in tensors, right? Input length. So either we can actually convert it to a tensor, probably 2096. So just to get an idea what each of these part means. Sorry. That is this part. This is we call token IDs, like I said earlier. So each of this represents each of these words. This image features a vintage of classical part means these of these are token IDs. So 2094 is actually represents this. 2471 represents image. 0965 represents features, like that, and so on and so forth. So theoretically, we can actually let's say transform the code. The code only. Two zero nine four. Let's see. Yes, correct. That means this gives the token IDs. So 2094 means that this and image features this image features a vintage or classic. Probably 653 will be classic. Or okay. That means vintage or 656 means or that means classic means 9760. Yes. So this is, like I said earlier, this we called token IDs. You decode it, then the output. And that's it. That sums it up. That comes up with visual language model. We discuss about large language model. We discuss about the vision encoder part. We can discuss about how we can combine it together. We can get the result done. Cool. If you have any kind of doubts, or I think, let me wait a minute. You can connect me on my LinkedIn to maybe connect me on there. And if you have any kind of doubts or something like that, just ping me over there. And we are actually based out of Kasargod, and myself, we are working on a lot of stuff. And currently, Conway Innovations, which is my company, is currently accelerated in Meta AI Accelerator. We're the top 5 startups from India under Meta AI Accelerator. And we are working on agentic AI systems, particularly like for researchers, kind of like current ChatGPT and Gemini doesn't have a lot of features. Currently, we developed an application that kind of works within your computer like a desktop app and kind of manipulate files in your PC like Cloud Code, like like other platforms like Cloud Code, or maybe like open code kind of approach. But more of a desktop application where you can create files, edit files, read a PDF files, a couple of PDF files to create docs, such kind of stuff. And you can get a lot of information about that in our website, conwayinnovations.com. And yeah, and also you can connect me on my LinkedIn if anyone wants to stay in touch with me. So if anyone has any doubts about today's sections on visual language model and transition transformers, you can unmute yourself and talk. We have around a couple of minutes. Hello. I think Shampakumar, you have audio is actually.
Participants, any queries, please?
Queries, if you have any queries, you can just unmute yourself or type on the comment section, or any feedback that you have to ask about it. You can just unmute yourself and ask.
Okay, there is no queries. Good afternoon, everyone. As we come to the end of today's session, I would like to express my sincere thanks to Dr. Nandakishore M for delivering an informative and inspiring session. We truly appreciate.
Pardon me
the
on that, just me. I'm not a doctor yet, so I'm just Nanda Kishore.
Doubt?
I'm just Nanda Kishore. You can call me Mr. Nanda Kishore. Not doctor yet. So yeah, continue.
Okay, okay. Okay, I would like to express my sincere thanks to Dr. Nandakishore M for delivering an informative
Again,
and
it's
inspiring.
not Nanda Kishore, Dr. Nanda Kishore. It's just Nanda Kishore. Okay, cool. Yeah, just me. Continue.
Okay, we truly appreciate the time and effort you have taken to be with us today. My heartfelt thanks to the head of department and all faculty coordinators for their efforts in organizing this 6 days FTP. I would also like to thank all the participants for your active participation and support. Once again, thank you all. We look forward to seeing you tomorrow for another enriching session. Participants, please note, tomorrow's session is morning 10 to 12. Thank you.